So our next speaker is Slavomír Sihelník, if I can get that correct, from Marisky University in Chechnya. He's going to be talking to us about atmospheric plasma pretreatment of ultra-thin flexible glass for the transparent organic coatings. A little bit of an introduction. Slavomír is a researcher at the Department of Plasma Physics and Technology for Faculty of Science at Marisky. I'm really sorry I can't pronounce that very well. University in Brno. His research focuses on applied physics with emphasis on surface science, plasma processing. His expertise includes surface analysis, surface modification, and applications of plasma in materials engineering. He's been involved in various projects related to plasma and nanotechnology, modification of float glass surfaces prior to lamination, and I will let you continue.
Thank you for introducing me. Good afternoon. Thank you for coming. I'm glad you are here and are interested in my presentation. It was a pretty nice match to select my presentation after Knut, because we both use the same medium for making some treatment or modification, and it's plasma, which is generated by electrical discharge. The difference is between magnetron sputtering and our plasma systems we used in our study, that we use only atmospheric air, not vacuum. So it's possible to be used for large areas. And that's why I worked with a flexible glass, which is produced on much larger areas than float glass, because it can be stored in the rolls, and then it's possible to be processed in the inline devices. Such flexible glass is interesting, for example, as an encapsulation material in electronics, which need high transmittance, so optoelectronic applications like flexible photovoltaics and sensors. This flexible glass has a surface with a high surface energy, so it absorbs the water and other contaminants from air, and it's covered with a very thin film, only few nanometers on its surface, and this can hinder some coating applications which needs to be bonded directly to the surface of glass or flexible glass. And so typically cleaning techniques use some solvents or mechanical brushes or ultrasonic cleaning, and they have some limitations. For example, if you want to clean the very fragile material, I worked with a flexible glass which was just 30 microns thin, so it was fragile, and the non-contact method for its cleaning was something which was challenging to overcome this problems which are coming from solvent-based cleaning protocol. And also this solvent-based cleaning protocol, which we used for our coating dispersion, was containing of more liquids like detergent, acetone, or isopropyl alcohol. And this is a standard cleaning protocol which is used in a chemical technology faculty in Bratislava, which we cooperated in it, and they prepared us the dispersions of PEDOT PSS. PEDOT PSS is highly conductive and transparent polymer, which is suitable for flexible electronics. And what is the problem in organic conductive electrodes for such types of electronic is that it's a very short lifetime, because it's much more degradable by humidity. And typically nowadays the flexible electronics are mostly made with plastic substrates or superstrates, and this can not barrier as much as, for example, glass can. So the high chemical resistance of flexible glass is a motivation to use as encapsulation material for organic coatings like PEDOT PSS. So, and the surface energy of the flexible glass is so low that normally the coating cannot be formed on it because it shrinks to small aisles and it's not uniform. And for conductive coating, you need uniformity of the coating to be without any defects. So that's why in a solvent-based cleaning protocol, there is used detergent, which contains surfactants, which can raise the surface free energy. In plasma, we just used ambient air. The plasma sources we used are non-thermal plasma sources, and it's because their discharge is isolated with the dielectric barrier or isolation material. We used a very thin ceramic, and then the current in this discharge is low, and also the temperature is low. Therefore, it's suitable for treatment of some very, very temperature-sensitive materials like foils. The plasma source on the right side is directly used in the industry for treatment of foils. On the left side, you can see a plasma source which was developed in Bratislava, and also we work in it in Brno, in Masaryk University, and it's called DCSBD. You see the configuration which is in a curved arrangement. Is because we want to implement it on a roll-to-roll system which can unwind and wind, for example, flexible glass. So on the next slide, what we use on both is air, and the power needs for these units, which have in both cases the width of 20 centimeters, is 350 or 416 watts. It depends what we used. So to come closer to this plasma source, which we are developed in Bratislava and is sold by spin-off company Roplas, has the electrodes inside the unit. You can see on this picture, and the plasma is generated above the ceramic. So it has very thin layer, which has very high concentration of reactive species generated in plasma, which can be useful for some plasmochemical modification. And we place the samples on the roll. That's why I show you this picture, because we see that this covering of the sample has an effect, because the plasma is in very thin layers, so it's hindered to burn over these holders of paper. And the reactor, which I used, is also suitable for use with another gas if you want to do some another application. But for cleaning and activation, ambient air become approved as enough sufficient. And the second plasma system is based on wettability, which has the electrodes directly next to each other. So it needs to be generated on a gap only under 2 millimeters. So for flexible glass, it will be fine. But for example, for some thicker foils, like for example are used for laminated glass, it's not enough space to 2 millimeter to pass the sample. So this has limit. Our previously shown plasma system has no limitation for the thickness of the coating, because you just expose the surface, only the surface to the plasma active area. And afterwards, we plasma treated flexible glass. I treated it with two methods. One is spin coating, which rotates the sample, and I just cast the drop on the sample, and it spread on the surface. And the second one was using the dual action airbrush, which is it has also very similar dose of the amount needed for covering the same surface, so there were comparable methods. And so how I analyzed my experiments. First, I analyzed the plasma-treated ultra-thin flexible glass. So we used methods for evaluating if it's activated, if the morphology was affected by plasma treatment, and try to find out what is behind the effect, so chemical changes. And then afterwards, I made the coatings, and then I tried to evaluate their qualities for transparent conductive electrodes, so I need to evaluate sheet resistance or conductivity for thickness, and also I was observing if the samples are uniform, because this is key for their performance. So first, the very fast method we use for the change of the surface free energy is make a drop of water on the surface, and if the surface energy is higher, it can spread more, which can be beneficial for spraying techniques that can save the material dispersion needed for spraying, because you can cover faster the larger surface with less drops. So, and even just 0.1 second dropped the contact angle of this drop very low. And after increasing the treatment time, which you see on the graph in the right, you see that increasing the treatment time doesn't induce more decrease of contact angle. So we chose that very short treatment time, which we were able to do with our DCSBD reactor, is enough sufficient for providing our experiments. And then what maybe is important if you are trying to involve plasma modification of surface to your technology, is that you need to consider that the modification is done only in nanolayer on the surface, and it's not so stable. So we, in different materials, we observe different recovery of this effect. So we then study still the aging. So for flexible glass, when the reference was like 79 degrees, the aging even after 1 month doesn't lead to recovery to the initial value. But we can see that after first 8 hours, it's not recovered so much. It's still around 10 degrees or below. But after then, maybe it's still rising. So you can see that for inline implementation, this cannot be the problem. But why I'm showing you this? Because we can see the difference between the exposure time and between the effects of plasma. And this is because there are more processes which are contributing on this effect. So let's first see that if we tested the comparison with water drops and drops of diamethane, which allows us to evaluate components of surface-free energy. And one of these components is a disperse, which is more by physical surface modification. It's the yellow one in the graph, and the blue one, the polar, is the component which belongs to functional groups, which we expect that we generate in plasma. And we can see that 0.1 second, which has much faster aging, the red line in the left graph, compared to the 0.5 second, which aged not so fast, then it can be seen that only the polar component changed. After 7 days, it was reduced more close to the half. So the instability of the coating belongs to the decrease of this polar component. And what about the change on the surface morphology? At the beginning, I showed you the picture where was the illustration of contaminants coming from air. And these airborne contaminants can be visible on the AFM analysis. You can see these traces of some liquid or the grease or very small film, which is just randomly spread on the surface, and it has just a thickness of around 1 nanometer. And after plasma treatment, which we applied in 3 seconds, because we are very interested, the prolonging treatment time can have some effect on the morphology of the surface. We saw that they are disappeared, and you cannot see these airborne contaminants. And the surface roughness it was unchanged in both cases. The flexible glass is very smooth, and it was evaluated as still not changed this roughness of the surface. And what is then if we didn't change the roughness? So what is behind the chemical change? So we did the XPS analysis, and this is the surface spectra of reference sample, which contains high peak of carbon and also the high peak of oxygen, which is naturally in every glass that you can have some oxygen in the silicon oxide structure. And the oxygen also can come from airborne contaminants and can come from the polar groups we are introducing on the surface. And to see the graph, when we compared the water contact angle, which very significantly decreased after the 1 second exposure, and the change in the ratios of carbon and oxygen and silicon and oxygen, can help us to understand how the content on the surface is changed. Because if you lose the STO ratio, it means that you are stop detecting the part of silicon, because the analytical depth of XPS for glass is only 3 nanometers. So some material is appearing on the surface, so STO is lowering. So this was for the plasma source which has volume DBD, but for DCSBD plasma source it was pretty stable, and similarly as in the reference sample it was not very changed. But then if we see on carbon and oxygen ratio, the carbon particularly comes for carbohydrates and from the contaminants on the surface, from airborne contaminants, and the oxygen is stable in the profile of silicon oxide because it's unchanged compared to the reference. Then the oxygen increased, so the ratio decreased as the result of these contributions. And the plasma is very fast, as you saw. So we analyzed this, also the changes in bonds of this carbon, to see how it's compared to the solvent cleaning protocol, which we used according to the recipe from our chemical colleagues, that we used this solvent cleaning protocol. So also this increased the polar groups, which are indicated by carbon and carboxyl groups. And also we decreased the carbohydrate peak, which is green one. And if we now see the plasma treated samples, the very, very similar looks the DCSBD plasma treated flexible glass surface, and the composition on the surface of VDBD changed. So this is some higher and unstable change, which is not similar to the solvent cleaning protocol. Therefore, we expect that DCSBD is more regular, and it's not so it's comparable, that its effect with the solvent cleaning protocol. And we applied it for the plasma treatment before the coatings. And first, the coatings on spin coater are rotated on same rotations, and it has the same time, and the drop is the same. So the sheet resistance was enough consistent to see the effect of plasma. So these are the graphs of sheet resistance. Because we expect that thickness is similar in these coatings, and we measured it, it was around 80 nanometers. And you can see that after 1 second, there was a very fast drop, and it was consistent for all conditions of rotations. We used plasma treatment and solvent cleaning protocol, and also we used the plasma and preliminary uncleaned sample. And the effect was quite similar, even if we not used the solvent cleaning protocol. So I can show you the next graph. And what is this trend is that the lowering the exposure time to plasma induced a better quality of coating, which is interesting, and it's due to the various processes in plasma then cannot be on the same time scale. And spray-coated samples are done with the airbrush, so I needed to evaluate sheet resistance and thickness of these coatings because it varied more. So this is the graph of conductivity. And also the conductivity showed that the shorter treatment time increased the conductivity of our coating of PEDOT PSS. So here we can see that even 1/4 of a second is enough sufficient to increase the conductivity from practically unconductive coating of the uncleaned flexible glass to very high values, which are very, very similar to the values of 3 liquids of solvent cleaning protocol clean samples, which is also due to the uniformity of coating, which can be seen on these pictures. And we observed that uncleaned reference has a lot of defects and the coating form small aisles. On the other samples, we can compare that, for example, we saw that we compared also with a roll-to-roll DBD, the blue line, and we see that the effect was faster with the DCSBD, and also the the conductivity was better for roll-to-roll DCSBD. So it's due to the effect that is the similar character of the plasma, and the effect of DCSBD due to the very thin layer was faster. So after 0.1 second, it was looking like samples of 0.5 seconds for roll-to-roll DBD. And this time was enough sufficient to prepare sample with a uniform coating with the DCSBD plasma. Visually, because I was showing you the papers which I needed to attach the flexible glass on the roll of our cylinder, this paper covered the plasma, and we can see the border of this paper on the coating. So I placed the paper in the plasma on the flexible glass and the treatment, and then I made a coating, and it showed that the parts which were covered with this paper were not affected by the plasma. So it's nice, clean result that the plasma is effective, and it's possible to see also with the naked eye. And it's not deteriorating the very smooth surface of flexible glass. The process is made only on the surface, and it's increased the oxygen-based functional groups. But it's in different way which is due to the character of plasma. So good plasma source needs to be selected for the treatment if you want to incorporate it in this technology. The advantage of this atmospheric plasma pressure systems that is that they are implementable to the roll-to-roll processing, which is flexible glass suitable for. And we can replace the solvent cleaning protocol, which is also very interesting for fabrication of flexible electronics. And thank you for your attention. Feel free to ask.
Okay.